Alright, so I wanted to just spend a few moments on the projects and talking about LT-Spice and MATLAB and all that. And then a lot of this won't make much sense right now, but it will in the coming weeks, I hope. So, but I do want to talk about it anyway. So all of the stuff from chapter 9, which is on the high-speed data converter, is drafted in Cadence uh, and Mentor and Silvaco and all these other tools. However, uh, it's not in LT-Spice. And if you go look in the LT-Spice folder, which I updated yesterday because I've been working on it, what is for these other, let's make sure we're recording, for those other images or those other figures is net lists. And that there's like figure 9.3, well, let's see, figure 9.3.4 here. That SPI is a net list. So if I open it up and look at it, what should I open with? Open. I don't want to open it. I want to open it with a text editor. Anyway, you'll see it's a text file, and it was generated from Electric, what I'm about to show you. So one of the things that's been taking me a while to get the projects posted is I've had to draft all of the LT-Spice, and I'm going to show you what I've been working on here before we get going. So what happens is, this is just a 1-bit topology, and there's 8 latches on the output, so I could use the same code for both 8 paths and 1 path. So as I was saying right before we started, if you look at the 1-bit code out here out of the clocked comparator, it's all common right here to the D flip-flops, and it's Q1I or invert because the D flip-flop is inverted. So I just did the simulation, I just ran it, and it looks like the following. One thing, this is a raw file. If you don't want LT-Spice to automatically delete the raw file when you're done, you have to go over to Operation, and where it says automatically delete raw files, select no, or else you'll have to rerun the sim again, which, as you saw, takes a few minutes. The longer ones, if there's 8 paths, takes even more. So now what I'm going to do is I'm going to go open the MATLAB script, and let's just pick the one in the let's pick this one, chapter 9, and I'll show you, like I said, in LT-Spice in just a moment. And this is the main one, figure 933 MATLAB, and here's the 1-bit version. Let's open that. Hold on a sec, I gotta put the raw file in that directory or it won't read it. Where is the raw file? Oh, I guess it is in the directory already. Okay, so you can look through what happens here. VDD5, your oversampling ratio. You'll become familiar with all of this, but what it's going to do is it's going to read this raw file, the one I just generated, from the simulation in LT-Spice, and then generate a bunch of other stuff. So I'm going to hit run. It's going to ask me to change a directory. And then it's going to run. What just happened? Oh, okay. It's just slow. So here you can see, all right, and again, I don't expect you to know how to do this at this point, but if you look, this is in parallel mode where they're all coming out together, what the symbols look like. This is in serial mode, which of course for this one is the same because all the outputs are tied together. And then you can look at, here's the, and again, we'll go through all of this. This is the desired tone. You can see the noise shaping. This is for the bandwidth greater than B. Here's the signal and the noise, and then you set the bandwidth with in the MATLAB script. So you can do everything digitally, but the thing is we need to make sure you know how to use the LT-Spice and how to modify things. Now, I don't want you doing a lot of transistor level modifications. If you want to do something modest, that's fine. I don't want you going overboard though. So these are there. So now let me tell you what I've been working on. It's not that great here, but it's only a 1-bit converter. So like I said, let me close this. We don't need to clear that. You can see what the bandwidth is and all that stuff. If I go look in Electric here, which is the layout tool, and I can go down and there's my raw file. There's my net list. I don't want to use electric. I want to use lt-spice because I don't want you to have to learn another tool. Okay, so what I did, and I didn't remember I did this or I would have fixed it, is I copied these net lists over into the lt-spice folder. So for example, figure 934, which is, let's see, what is it? 934. Okay, it's this figure right here. That's generated here. This one is copied over and then just sitting there in the directory. So I want to show you. So I go close this. I'm going to close the electric, this one. So it deleted it. Then I'm going to go into lt-spice. Here, let's do it from scratch so you can see. lt-spice, chapter 9, and then I go to the very end, and you see the ones with the transistor symbols? Those are actual schematics. If I go down to the bottom, these are MATLAB scripts. If I go look here, where is it? 9, oh, it's at the top, sorry. So 934, you see this right here, 934, 934, 935. Those are net lists. Why can't I open with? Here, let's cheat. You can see this is a net list, and I don't want you modifying. I mean, you can. I've done them, thousands of them, but it's easier just to do things with the schematic. So what I found when I was making up your projects is there wasn't symbols for all of these real transistor level stuff. So yesterday I drafted, let me show you a few. Where's clock gen? That one was good times. So there's the clock generator, and if you go inside, it's got stuff, and they're all transistor level stuff. Where's the clock gen sim? That's like figure 921. No, this is ideal components. Now this one, ideal components 925. Yeah. So here's the clock generator. So it uses actual transistors, so there's nothing ideal in there. And so you could go in and modify that to generate the clocks you want. You notice this one generates, if I were to, there's phi11, and then if I look at the complement, oops, phi1, and then if I look at the phi2 one, you see they're non-overlapping. So for switch capacitors, I've got 8 different phases of clocks and all this stuff going on there. I can push in there and see what's going on in each one and show it. All right. So there's that, and then there's this one, which was a amplifier. It's a self-bias amplifier. Again, I don't expect you, that's not what we're learning in the class, but you look and you say, okay, that's the step response, and it has to be pretty fast for high-speed operation. It has a 400 femtofarad load. Then this is the clocked comparator, and I'm sure there could be work done on this to make it simpler or better, whatever. But here it shows where V and P crosses V and M. After a little bit of a delay, the output goes high. So it's a clocked comparator, and you could go modify it. You could say, oh, I want to go from 5 to 0. Whoops, no, that's not what I want. I want 2 to 1, so the rise time goes the other direction. So hit OK. So the green, you'll see it's going the other direction now. And so it goes back low. And then, what's that? It's C5. So here's where I left off, and I want to show you what was happening. So in this topology, so all of these, so here's the switch capacitors, here's the amp, the clocked comparator. So this is one path, and so this is where I've decided I'm not feeling well enough after doing this for 6 hours to continue on, because it's ridiculous amount of drafting. It's not like in tools where you can create a bus or whatever. You have to physically label. You can't say create icon or create symbol either. You have to do everything from scratch, and I'm going to do that today just as an example for you. But I want to show you something. So here you see Q1, coming out, and you see it's connected here, and then it goes out. So let me show you what happens when we run this. And I should have ran it to begin with. But what's going to happen is that this logic in here is made with ideal switches, and they don't interface well with transistor level stuff. So there's a problem in the D flip-flops, and I'm going to show you that because it works. Well, maybe it won't be on this machine. There was on my machine. But it works great to start out with. You see we're getting nice 0 and 1s, and it looks reasonable. Everybody looks at this and realizes, oh, it's low here. That's what we expect because it's a moving average of the analog input. Here it's high most of the time. That's what we expect, etc. But around 2 microseconds, it starts to die. So I went over and looked at the corresponding schematic here, and what's used, what's used is the following. It's this circuit right here, and it's a dynamic circuit with 2 inverters. I put those just so I'd have really good logic levels. So what I want to do is I want to make the symbol. I want to make this using LT-Spice and make a symbol, and then put it in the sim. And then by Monday or whatever, I'll have the projects done, and I'll decide how we're going to handle the using transistors versus ideal components, because it becomes more challenging with ideal components because you have finite delays, and so it's a better project. But it's not reasonable if the prerequisite to the class is signals 360 and electronics 320 if I ask you to do analog design, okay? So we'll go make this in a moment from scratch, and not seeing any issues so far, so maybe it'll be fine. Let's go ahead into MATLAB and close this, and then let's do a CLC. Clear all. I think I did that all. Whoops. Hope there was no variable LL. Alright, so I'm going to go open, and then I'm going to go to my desktop, LT-Spice, chapter 9, and then I'm doing, so you have all these already, and they all work fine if you want to play around. Here's the one we're going to finish drafting. It comes through, and you can actually run the sim before run it before the simulation starts. Of course, you won't get good signal to noise ratio or any of that. So you say, okay, because it's not finished. Okay, so let's go see where we're at. Okay, it's not dying yet. What I saw in what I did yesterday is that above, well, of course it was a little bit later than this, above 2 microseconds or whatever, for some reason that D flip-flop would go, because I don't care if you use an ideal D flip-flop to resynchronize the data, that's not important. The D flip-flop would go to this 2.5 volt state and sit there, and I'm like, what the hell's going on here? And I played around with it for a while, and I'm like, oh, this is some issue with interfacing real transistors with ideal components, and it's just not, because you're not getting fast edges like you get with ideal components, you're getting slow edges. It's not working out. So we'll see what happens. No matter what, we're going to draft the schematic so you know. Has anybody in here actually drafted a schematic or a symbol from scratch? Not copying one that's already been... You have? No, an LT-Spice. You have? Okay, so what was the big issue there? What, I mean, for me, there was one big thing that you need to know about drafting a symbol. Well, the names have to match, but of course. What's that? Pin table. Yeah, the pin table, right? Because if you don't know the pin table, it'll only take me a few minutes to draft these, so I'm going to do it just so you can see. Well, you assign them, and that's right, but the problem is if it goes in the pin table like 1, 2, 4, 5, and you don't have 1, 2, 3, it doesn't work. It just won't work if they're not continuous numbers. So I want to show you that. Yeah. So let's go ahead and run the sim. It doesn't look like it failed for some reason. It seems like when LT-Spice warms up, it starts failing. So I don't know what the deal is. What? Maybe it did fail. We have negative SNR. I must not have something connected. Let me go back and look. Clock Q1. So let's troubleshoot. Let's look at V7. Looks good. Let's look at clock. Should be a little delayed. It looks good. Rising edge. What else? Should be the same. It looks identical, which is what it should. Eight-bit hold register QI. Let's make sure those are all the same. They are. Let's make sure this isn't connected anywhere. It's not. Okay. Oh, let's look at the output because I played around with this capacitor. That's fine. Oops, something's wrong. So that says, oh no, that's right, P1I. P1I. Okay, that's fine. These labels are different, but that's fine. It is clocking, right? Yeah, I did clock. I did hit clock. Let's look in the MATLAB script. Clear all, path 8, OSR 64, VDD 5, figure 933.1. What's that? Yeah, you basically, the scripts, wait, what was that? You basically say when clock's above 2.5, it's a 1 or any of the bits, and so you can go through and see what's going on here. But what the hell? I did this yesterday. Something's not connected right. B0, B1, B2, B3, B4. Let's go look in here. Clock, wait. Oh, that's right. Clock, P1. So this gets strobed at the same time as this, so it has basically a whole cycle, so that's right. Integrator, that's right. And if we look at the data, wait, something's wrong. So B7, B6, B5, B4, B3. Clock, V, and B. Okay, we got to make sure you label it B for that data. I just did this last night right before I zipped it up, and it had problems with the 1 zeros, but sometimes it would work. It was really weird. Oops. Let's find out. Yep. Here, let's do this. What's that? Yeah, that's what I'm thinking. That's honestly what was in my mind. Clear LL. Oh, what is that? Clear linked list or something? So chapter 9, MS3. Where's the start button? It's killing me. Killing me. Or the run button. Nope, same exact thing. Does that look the same? VN, let me make sure it's VN. VN, do I have save VN? Yep, right there. Save P1, do I have save V clock? Yep, right there. How is that possible? Tell you what we're gonna do. Let's do a control C. Then go over here. You know what? I know that's not the problem. Why waste time? Let me look at the script one more time. What I'm thinking now is that there's a problem with the setup where it's using some funny loop here, but it didn't have that problem with the other one, did it? Well, I'll play with this weekend if I can't figure it out in just 2 seconds. B0, B1, B2, B3, clock, int, 4, 5, 6, 7, VN, pause, min, P11. Let's do this. Let's look at that. And then look at that. They should be complements. And they are. That's irritating. Well, that's what I was saying. I had a problem with it going, but I'm not seeing that. What I had before was there like pedestals right at 2.5 volts. What bothers me is I just did this last night. This same exact file. These are I saved. Look at the date on these. If you go in here, chapter 9, you look at that figure, that one's 31 1-bit. This thing, saved last night, 10:23, 7:51 p.m. So how could it magically stop working? What's that? No, I didn't touch that at all. No, I was doing it at home. That's why I'm wondering if there's a problem with the setup here or something. But I got plot options, win size, so I'm not skipping anything. I'm skipping, well, I skipped the 100 nanoseconds at the beginning. Let's try one last thing and then we'll stop. Let me try making that 400. What I'm worried is the integrator's saturating. Didn't I say V positive? Right there, why isn't it letting now? Alright, there's something funny going on. I guess that's the point, right? Maybe there's something funny with the digital data. Does everybody see that? It's going 0, 2.55. So that's the problem. I mean, I didn't see that in the previous data, but I don't know. What's that? No, it's the ideal latches. This data comes out of the ideal latches. If you go back over here and you plot Q1, okay, it looks fine. I mean, it looks like real data. Because it's from a transistor. Then you go look at the outputs here. I don't know what the hell's going on here because there's not even a clock signal in this time. So that was the point. Well, the clock is right here. Yeah, so something funny's going on, even though it's a full logic level. Okay. Which block? This one? This one? Yep. This one? It works fine when everything's ideal. It's just when you have other components there, it's not working. So, jeez, we're burning a lot of class time. Do you think we should go through that or not? The drafting of the flip-flop. Yeah, you don't want to go through it. Okay. Well, the problem is if you haven't had LT Spice, it could be very useful. I know I've had some students that say, I don't know, I've had problems with the schematics and using it, like the pin table. Yay or nay? How about you guys? You want it? The draft, the schematic? You don't? All right. So I'll work on that and get everything working, and then I'll send an email out to the class, and then you download it. And you should know enough right now how to run everything. Okay, so you can run up these, and just for I'll figure out what's going on. Just for if you want to look at the beginning sections, the earlier ones are all ideal, so they run a lot faster, and you can see what's going on there. See, they'll run fast, and there's scripts for doing certain things with them and all that. You can play around, but those are ideal components. But again, I'd prefer you not use ideal components because that's not as hard as using components which are transistor components, okay? So, all right, so play around. We'll stop there. Okay. I'm still trying to narrow it out. What I'm thinking right now is to take the topology, and I was looking at SerDes and all that, but it kept coming back to the prerequisite to the class isn't analog design, and so then you'd have to do everything with ideal components, which is, in my mind, a little academic. So then I'm thinking, well, instead of doing a switch capacitor design, you do a continuous time design where you have to adjust the feedback pulses, which are continuous signals rather than switch capacitor. There is a student of mine did a couple years ago something similar, but it's not using resistors. It's, I'll show you. Where is it? This one. So this is, and we'll talk about it today. Here's what's in the book, right? It's basically a K delta. It's got switch capacitors here. They'll sum up into the integrator, and you go from there. And then, here's the discussion of putting delta sigmas in. Then here's the discussion, the introductory stuff about you want true noise shaping. Here's some discussion, so if you get a chance, look at this, on continuous time delta sigmas using resistors. The issue here, as I mentioned, is that this guy switches and then provides a feedback signal for the entire slow clock period. Then the next one switches entire slow clock period, etc. So you basically got a whole bunch of worthless information, because after the first part of the clock cycle you're sending back, that stuff's meaningless. So you need to adjust the feedback so it's only sending back a chunk of charge. So one way to do it is with like a simple set reset circuit, which goes to a high Z state, and I can sketch one for you. But he did in this one, he said, I'm going to still use a capacitor, but I'm going to use an alternative way of getting rid of these resistors. I'm going to use this. And what I would prefer, so you don't have to generate non-overlapping clocks or the clock generators, is to use resistors and control the feedback signal to the resistor. Does everybody follow that? So let me sketch what I'm talking about. So you got, so this is, what are we supposed to talk about today? K delta 1 sigma and active. Actually, I think I'm going to move on to active because we're running out of time. I'll talk one more time about K delta 1 sigma active integrators. So basically, if you take this circuit right here, okay, so let me ask this. Does everybody understand that if S is high and S bar is low, this is a TG and it just connects this side to this side, right? So if I put this at VDD and I turn this on, it drives this to VDD. If I then come down and I do just the opposite, and this is S, and this is S bar, and I connect this one to ground, so you can already say, well, I don't need to have two transistors here, I only need this one, right? And I don't need to have two transistors here since I'm going to ground, I only need this one. So you could connect these two together, and then with some logic you could say, I'm going to make a decision. The decision's going to turn on and turn off, and it's going to turn one of these gates on, and you can feed that to a resistor back to the integrator. Now there's several issues here to make this practical. So you don't need non-overlapping clocks. You do need phases of a clock, but I don't want you to worry about that. I just want you to use a ring oscillator of some kind. So here's your V in, and so it comes in, and here's your comparator, but we'll probably use an active integrator from this point on. And so your input signal's coming in, and say this is tied to VCM. So ideally this is sitting at VCM, and it's your input signal's coming in here. You feed back an amount of charge into this input, which on average is equal to your input signal. Now there's a lot of issues here. One is you're not going to have necessarily a one-to-one correspondence between what your digital signal you read out is and your analog input, because you're not feeding back a signal which is exactly, I mean, the analog part is going to be exactly equal to here, but the levels and the correspondence, I think there'll be some offset, but you don't care. You don't care if it's got a gain problem, because gain issues are trivial to fix digitally. You care about if it's reproducing the input signal correctly, okay? So you chunk this charge, your comparator makes a decision, and it says, oh, select this TG, or if it's too low, it says, hey, select this one to add or remove charge. So you have the K paths that do this, and then you have a fixed width that comes in and adds. Now, one other issue is these have finite resistance. So if they have finite resistance, it's in series with this resistor here, and affects how much signal you feed back. Okay, so that's an issue. Another issue, is everybody following me so far? So this is like, I'm going to take my cup and I'm going to dump a certain amount in. I'm not going to let it go the entire clock period, okay? One other, and so it's all resistors, no non-overlapping clocks, but if you look at the example, and like I said, I'm trying to get everything, but these little issues, and hopefully I'm trying so that you don't have them when you do the design. I think it, again, is because of ideal and non-ideal components. But if you look at the clock generator that I don't want to show you again, that I built, I put in stages so that I could have an even number of stages. But if I have a ring oscillator like this and I have an odd number of stages, let's just do a 3-stage, right? You're not going to have the situation where you have 8 evenly spaced edges. If you did 7 or you did 9, you don't have 8 evenly spaced edges. The problem is if your edges aren't evenly spaced, then what happens is you can get the effects of clock jitter. So you say, okay, I've got 8 edges, and the final one I'm just going to ignore that last edge. Well, you have this big clock jitter issue here, right? And the problem with that is you'll get amplitude modulation in your output. You'll see when you do the project. Your output will be reconstructed, and then you'll look at it, and it'll be like this. Here will be your input. Your input will be like this, nice and flat, and your output will be going like this. And then the amplitude will be modulated. So you got to make a ring oscillator. That's one of the reasons I put that one in there that doesn't use an odd number of stages. So you basically have to use like the NAND gates or something like that with the cross-coupled feedback, okay? So just like I had in there where it's the latch, you feed everything back and it gives you nice, well-defined edges, okay? Are there any questions about that? I know people aren't following, so let me just show you in a simulation. So that was 25. So here's my clock generator. There's the 4 stages. I still need odd feedback, but there's probably a better way to do this. I've got the outputs. Now remember, if I do switch capacitors and 8 paths, I need a lot of clock phases because I need true and complements. So I don't need anything this grand, okay? The only difference between this inverter is it's a 3015 and this one is 6 and 3, so it's a smaller inverter. So you have to modify these. But if I go look at the output and I look at the edges, if I look at the first and the last edge, let's go, let's drop that to 0, or let's do -6 as well. Actually, let's get rid of all of these. That's exactly what I didn't want to do. If I just now go look, and I just plot boom, boom, I think that's right. 4 phases, and I look, they're all spaced evenly. You don't see any space where there's a gap wider in one than the other. Does everybody see that? Now, keep in mind also the effective sampling frequencies, the distance between the rising edges. And this is an old process, and this distance is roughly 500 picoseconds or 2 gigahertz. So even in this old process, you're able to do gigahertz level sampling. It's pretty significant. Does everybody follow that? Okay. All right, so I've thrown a lot at you. Hopefully a little bit makes sense, but I'll nail down the project details. It's like I said, it's a tremendous amount of work to make sure that it's meaningful and you're not frustrated like I had that experience right at the beginning. I mean, that's just a total waste of time, right? Why won't it give me the right answers? And then you do change something and then you start getting the stair steps and all that. All right, is everybody totally confused? Yeah? Okay. It'll come together. And like I said, I think I said, I'm having deja vu. If you look at the course schedule, oh, I didn't put it in here yet. Next Friday, what I'm going to do is I'm going to spend the whole lecture talking about the projects. Okay, so just going over things and making sure everybody. So then the projects will be due on the 1st of December. Next Friday's October 31st, so you have a whole month. So it should be reasonable. Okay. You don't need to have a Thanksgiving anyway. Is he serious? Okay. So, do we need to talk about the K delta stuff anymore? Let me just go through some basic questions and make sure everybody's on board. So, first question I was asked right before, why is it 4R versus R? Yeah, so the gains are the same. So the effective feedback signals the 4Rs in parallel, and there's 4 of them, so 4Rs in parallel are R. What does the added amplifier do? Yeah, so it reduces the offset of the comparators. You could argue, well, can't you have the amplifier in series with the comparator? Sure, but then it doesn't reduce the offset of each comparator. The way the added amplifier is there, is the offset of it is common, and remember, the actual level isn't that important. Now, when you go through these sims, so basically this is adding all the bits together, and they're coming out at a rate which is the clock frequency, the slow clock, say 100 megahertz times 4. So the bits are changing at 400 megahertz coming out. But you still have to look at, when you add all those together to get a 2-bit word out, you still have to look at them as that is an averaging filter. Now, if you notice in the sims that I went over a moment ago, where I had all 8 bits in parallel, you can read those out in MATLAB and then read them out as though they're serial. So there's a way to trick it so that you can get really narrow high-speed bits out in a serializer, then basically treat them as though they're coming out serially and not parallel. Okay. Let's see what else here. Yeah. No, it doesn't. So what I used here in the sim, I think, well, I probably used a voltage control voltage source, but what you could use is you could use that amplifier I showed you, the self-biased one. That would work fine. The issue with the self-bias is you got to be careful about the input common mode range not falling within the range that you want. Now, a little caveat here, when you do these sims, everything looks great. And the reason is, and you do the MATLAB and you pull out and everything matches theory perfectly, and the reason is because you're using ideal components. When you start to use non-ideal components, meaning the comparator doesn't make an instantaneous decision, you start to get reductions in signal to noise ratio, and you start to have to do things like resynchronize the bits out here so that they come out without having metastability problems. Okay, we'll cover this more later. Let's see, anything else? Oh, so remember that, just to make sure it's clear, when we doubled the oversampling ratio for first order, we got 1.5 bits increase in SNR. When you use K paths, or you double the number of paths, it's exactly the same. You get 1.5 bits increase in SNR, 30 dB improvement, okay, or what is it, 9 dB improvement, right? So if I have 8 paths versus 1 path, that's equivalent to, you know, a doubling of 3 times. So I'd expect 4.5 bits increase in resolution. Now the benefit there is that you're also assuming the same bandwidth. If you don't assume the same bandwidth and your bandwidth goes out, then, you know, if you extend your bandwidth, then you're going to have a corresponding reduction in signal to noise ratio. Okay, so are there any questions on this? Okay, so what I want to do is spend the rest of the time on improving the linearity using an active integrator. And basically, what we're going to do is, instead of using an integrator where the capacitor goes to ground, we're going to use an active integrator like an op-amp. And the benefit there is then Vint ideally is 0 or very small, and so we get less distortion in our output. So the first one I want to look at here is this figure 629. And let's derive this, and then we'll look at some simulations. So what we have is we have our input, our Vin. So practically, this is the way a lot of the modulators are made. Oops, and then we have our feedback resistor R, the common mode, the DAC with the inversion, minus V out, V out. And then we have this going into the minus plus VCM. This is our clock frequency. This is our output. Okay, why did I connect this minus sign to the output instead of the plus sign? Well, my feedback, it's so my input and my output are the same polarity. So I get a minus inversion here. It's an inverting integrator, and I get an inversion here. So the input and output are the same, and then I invert the output here with this integrator, with this inverter. So let's go right now. Do you want me to do it in terms of the common mode voltage, or do you care? Let's just write Vn over R. Yeah, I don't have to do that. And then I could get rid of the inverter and try to use the output directly, but the problem is then my output would be inverted, which isn't a problem digitally. It's just when you're learning, it's easier to see things matching. And so the current going in here is what? From here. Yeah, minus V out over R. And when that current flows through here, so let's see, this is at, let's just say AC ground. So I have a capacitor with a current flowing backwards through it. So this voltage would be 1 over j omega c times minus I. Does everybody agree? Because it's flowing back. I know everybody that's taken analog from me agrees. You guys are all three of you are going, but you guys agree here. If this is going up and I have, well, let me do a simpler. If this is R and going down, this is plus minus and this is I, then you would agree this is I times R. Everybody would agree with that? And if I flip it around, see, I know this is a hard concept. I don't know why. That's why I hit it so hard in analog. And this is I flowing like this, and this is minus I times R, which is V. Yes or no? Is it good? Okay, so this would be minus 1 over j omega c. So this would be minus minus I times 1 over j omega c. And that I'm going to call Vx. So this is Vx. Tell me how to proceed. Well, plus VQE of F, if you want, equals V out. Everybody would agree? Oops, I got a sign issue somewhere. V in over R, V out over R. Vx is minus 1 over j omega c plus, minus VQE, because it's minus going in there. Not that it matters because VQE is random, equals V out. Still got a sign issue. Well, let's continue. We'll see what it shows. So we can rewrite this as minus plus. Then we move this to the other side, and what we have is minus Vn over j omega Rc minus VQE equals V out times 1 minus 1 over j omega Rc. And let's multiply the top and bottom, both sides by j omega Rc. So this becomes V out times 1 minus j omega Rc. That's whoops, how's that? Good. And that's minus VQE times j omega Rc. And that's just minus Vn. So I got a sign mistake because Vn's not going to be negative. Oh, right there. So this term, the Vx also gets negated when it goes through. So this everybody follow that? Because it's going through and being inverted as it goes through here. So this becomes positive Vn j omega. So let me write it better on the next page. So we get Vn. VQE, is anybody bothered if I just write it as positive? Because it's a random variable, it's going to be sometimes above 0, sometimes below 0, but since it's random, it doesn't make sense to say it's minus VQE. So plus VQE times j omega Rc equals V out times 1 plus j omega Rc. No, because minus V out and V in, and it goes in here, but then once it, which this is correct, but once it goes into the minus terminal here, it gets inverted again. And so last but not least, the useful thing is V out equals V in divided by 1 plus j omega Rc plus VQE times j omega Rc all over 1 plus j omega Rc. And so tell me what that means. Yeah, input's low pass filtered, output noise is noise shaped. It's high pass filtered. Okay, so, and that's what we had before, but when we had the passive integrator, we also had the distortion term, which was bad. So let's look at let's look at 631, a version of 631. And 631 version 2. I don't want the digital filter because it takes too long to sim. So you go up and you see, okay, and I think I showed you this already, how nice it looked compared to the passive modulator. Okay, and then we can also, while we're here, look at 630. And you can see how it's following. It looks good. Okay, are there any questions on that? I want to cover the second order noise shaping modulator real quick. All right. So the second, I'm going to talk about, I'm going to actually just point to it in the book since I want to make sure we're done with this chapter tonight. So I'll do a quasi PowerPoint topology because I know students love PowerPoint. So there's my second order noise shaping. I use 2 integrators. And I get, we'll see, I look at the response and notice because I have to have negative feedback around each inverter, I have to have an inversion when I go back between here and here in order to overall have negative feedback. So when I go from my input signal to my output, I see inversion, inversion, then I go on my output. Now, if you look at this, and you look at the signal transfer function and the noise transfer function, it's second order. And if you don't select the resistor and capacitor judiciously, you can have instability. And if you try, for example, to get rid of one of the paths, like right here, to try to simplify things, you get rid of this path. Just have a single feedback path so that that R goes to infinity. Well, you tell me. Looking at these, what do you see the issue is? Well, look at this right here. Well, I should cover this up so you don't have the answer. Since the poles will fall right on the y-axis, the topology is going to be unstable. You can't put poles, especially in analog circuits, right on the y-axis and assume it's going to be stable. They're going to hop over into the right half plane and cause instability. So now then you ask, well, how could I modify this to make it simpler so that I still get second order noise shaping? And that's what we did here. We simply put a proportional plus integral PI kind of filter right here, and you go through and it gives you can move your poles away from the unit circle, or around, I'm sorry, away from the right half plane, and you get a decent topology. Let's pause for a moment and look at the simulation of that. And so we can run it. Run. So let's see what happens if we do the following. Let's see if it'll go unstable in this topology. Did it? Yeah, it did. Does everybody follow? So I sorted out the resistor so that my poles are right on the y-axis. So when I put the resistor back in there, and I hit run, it starts to work again. It moves the poles away from the right half plane. Are there any questions on that? Because it didn't follow the input. Yeah. Yeah, and it went to the rails. But here, let's more appropriately, because it's not related to anything. So if you go run this, you look, you say, okay, that's happening. But watch what happens if we sim it longer. Let's do it. Whoops. We don't want that. Let's do 10. It's kind of just random. I mean, there's a little bit of an influence of the input on the output, but it's not at all following. It's basically bouncing back and forth between the rails. Okay. All right. Let's see. The last thing I want to talk about is the signal to noise ratio, and this is stuff we've already covered as well. Whoops. So if you look at here, you guys want me to write this down? I mean, we've done this already. It's the same exact thing we did before. So if you go through, you can see that for the first order modulator, let's see, which one are we doing here? Well, this is the second order modulator. Did I do the first order? For the second order modulator, just like before, we get 2.5 bits increase in resolution or 15 dB increase in SNR ideal. And then you can look at the order of the decimating filter that you need. It's basically 1 greater than the order of the for the switch capacitors. Log times base 2 for 16. Wait a sec. That's something I kind of glossed over. oh, k equal 4, 2.5. So if L is second order, to estimate the order of the decimating filter, 50 log k. Wait a sec. Why is this one different? It's saying the order of the decimating filter same as the order of the modulator. So here we have k is 16, but we're using two filters and the second order response, and here you see the simulation results. We're going to see in the next chapter that you use 1 plus for the other modulators, but let me just make sure I'm not having a brain fart and that's wrong. Yeah, I don't know what the deal is. It's 1 plus the order of the modulator. So why did I get to estimate the order of the decimating? Well, of course, you can always use a higher order and get more filtering. It just takes more area and more power. So log 2, so k is 4. For every doubling in k above 4, so if k is 16, log 2 would be, that would be 4, 8. Okay, I guess that's just the way it works out for this continuous time topology. Are there any questions? So I'm going to work on your projects, try to get them going. You probably don't have too much homework to do. It's good. Or you feel like you're getting ripped off. Feel like you're getting ripped off? All right, well, I think the projects will make up for it, especially if the sims don't work. All right, have a good weekend, and like I said, I'll email as soon as I get the stuff updated.